it was like 5 seconds for me to get back to here. Let's get started. I'm going to skip over a bunch of stuff here because I don't need to really worry about too much about it. You guys learned about some of the people that have explored space for us and seen the been on the moon and those kinds of things before. So we're going to look in this topic about things that we use to go and look at space. We're going to talk about how do we know how things are moving in space. We're going to look at the distribution of matter throughout space and the composition, like what are our planets in our solar system made up of. And so I'll put up some fun videos to go along with this. But early views of the cosmos, like back in the day, people had some pretty crazy ideas about what space was. But again, when we think about them not having access to, rockets, pretty commonplace today. Everyone has a rocket. There's a guy in Edmonton who built a car with twin jet engines, and he can, do crazy stuff like that. This happened in his garage. Back in the day, like this First Nations people who thought there was some guy that had basically like a parachute that he was holding up by a staff in his stomach. Today we look at that as being crazy. But when you don't know, when you can't get out and see, when you can't see the bigger, wider picture of things, that kind of idea might make some sense. Anywho, some societies, we learned about the Aztec last year, are fantastic. They know a decent, actually a pretty serious amount about how the cosmos work and where things are going and how things move. But there are a couple of words in here that are important. Solstice, sol, the prefix of it is like sun. It's the Latin word for sun. Stis is like stop. So when we're looking at solstice, we're looking at the longest day of the year and the shortest day of the year. So the summer solstice is the day when we get the most sunlight, and the winter solstice is the day, like up here, we get I think on the winter solstice, we got 6 hours of sunlight or something crazy like that. So those 2 days on either end of the calendar, they are the longest and shortest days of the year, sol being sun. And then we have, again, I hope this one is much more obvious to you, equinox. That prefix in equinox is equal, and that's used in math to say this is the same as this. So when we're talking about equinoxes, we're looking at days that have the same amount of day as they have of night. I hope that's not earth-shattering for you. But all sorts of societies had really, really, really thorough understandings of how these things work. When we talked about Tenochtitlan last year, we talked about the idea that the sun rose on the equinox between the 2 towers on the Tlaloc, the rain god's tower, and the and Huitzilopochtli, the sun god's tower. The sun rose perfectly in between those on the solstice or the equinox, and I can't remember which one. But it's like people had really great ideas. If you go to Stonehenge today, they still are it's still bang on accurate, and people are able to go and know more about when is a good season to be planting, based off of the sun's activities and how those things happen. So again, going back to grade 8, we talked in grade 8 about a geocentric model of the universe. That geocentric model means that the Earth is at the center and the sun and all the planets go around the Earth. Eventually, thanks to some wonderful scientific work, we eventually end up with the heliocentric model. And that heliocentric model, this is Aristotle's model. Aristotle, I watched a video where they said that Aristotle was one of the most influential thinkers in the world, and it's true. Aristotle massively influenced the way that people understand and think about the world around them. But the Aristotelian logic in this one just isn't right. The truth is the heliocentric model, which Copernicus figured out, is accurate, and it has all the planets revolving around the sun. The sun in its mass, I want to quickly just kind of lay this out there. This is extremely inaccurate, this picture. Do not base your ideas of things on this particular picture, because this particular picture is crazy wrong. Like the distances between things on here is so out to lunch, it's not even funny. So like, but as a model with the sun in the middle and Mercury and Venus and the Earth going out around it is accurate. The distance between Mars and Jupiter is insane. And I'll put up a really good video about our solar neighborhood here today as well. The other thing is the Earth does not go around the sun in a perfect circle. There are periods of time where in the Earth's path around the sun that we are closer to the sun, and there are periods when we are further away from the sun. So we have, and that is not what causes, some of you guys are going to get a mistaken idea about that. This is not what causes seasons. This does not cause seasons. Okay, so I'll talk about seasons a bit later on here. Carrying on, going back to technology, we now know more about the sun and the stars and the planets than ever before in history. This is a cool little bit. The sun's 149 million kilometers from us. And if you were to get on a 747 and travel at 965 kilometers per hour, it would take 17 years to get there. Now, at the speed of light gets to us from the sun in about 8.5 minutes. I think it's 8 minutes and 26 seconds or something silly like that. So, various different things that people use throughout history, not supremely important, just as long as you recognize that there is an evolution for these various different tools to go from the early years to a more modern satellite that we would use today. Okay, so we're going to talk about ways we measure things in space. So the first way we measure things is an astronomical unit. So an astronomical unit is the distance, the average distance of the Earth to the sun. So one astronomical unit, and we use astronomical units inside of our modeling of our solar system. So for example, Neptune is 30 times as far from the sun as the Earth is. Jupiter is 5 astronomical units, so it's 5 times as far from the sun as the Earth is. Okay? Mars is only 1.8 astronomical units from the sun. It's not that much further out. So these astronomical units make sense to use for things that are inside of our solar system. We don't use a light year because Pluto, the farthest object from the sun, is like 0.0000004 light years or something stupid like that. So, light years is the other thing that we use to measure the distance for things in space. And we use light years for objects that are substantially further out in space. So when we talk about how far away the closest star is, we would talk about it as being light years away. And light just means the distance that light travels in a year. So light travels at 300,000 kilometers per second, and that means in a year, light will travel 9.5 trillion kilometers, which I don't know if you know math well. That's a big number. So if you wrapped one light year around Earth's equator, it would have to wrap around approximately 236 million times. That's crazy far. And the Proxima Centauri, the nearest star to us, is 4 light years away. Like, that's crazy. So we don't actually, we measure inside of our solar system in astronomical units, and we measure outside of our solar system in light years. Okay? Excuse me. I'm going to put up a really good video on our solar system. This is kind of fun. If you want to go to a field, I know you're not supposed to be outside and going, like, you could do this alone in a field. Right now it's kind of snowy, but you could try it out. So if you were to go and put an object in the middle of your field, how big was that? I'm going to put up a really good video. It's just too perfect at doing this. And that's the other thing. When you're looking at an object out in deep space, you are looking, like if you're looking at a star, there's a thing right now, there's Betelgeuse, which is dimming, and scientists are thinking that it's possible that Betelgeuse, which is a star out in deep space, may well be getting ready to die. So, kind of exciting. If it does go supernova, it's a big star. If it does go supernova, we would see it as bright as the moon in the night. So it'd be kind of cool. But that's happened. If that were to happen, that has actually happened hundreds of years ago. Like, it happened hundreds of years ago is a gross exaggeration. It happened so long ago that it's crazy, because we're just talking about light traveling at that speed. So I forget how far away Betelgeuse is, but it could be a couple hundred light years that it took the light to get there, from there to us. And so what we're seeing, if it does go supernova, is we're actually seeing something that happened a couple hundred years ago. And so when we're talking about light years, even Alpha Centauri, which is the closest one, if it were to go supernova, we're actually seeing something that happened 4 years ago, but because it took so long for light to travel from there to here, we're seeing 4 years in the past. So that's kind of cool as far as I'm concerned. Yeah, that's the end of that one. Nothing too crazy. Distribution of matter in space. So we're going to talk, I'll put up a really good video about various different stars. Our star is pretty teeny tiny. Now, there's two different ways that we measure stars. We measure them in overall size, and we also measure them in heat. And so the color that they burn is the heat that they are, and then there are just crazy huge stars. And I'll put up a really fun video about different stars out in our solar system for you guys to be able to see that. Now, this right here is the way that popular theory of how stars are formed is from a nebula, which nebula they call a solar nursery. So basically there's a whole big pocket of gas out there in space, and that pocket of gas, eventually the particles, when one particle bumps into another one and they stick together, they now have twice as much gravity as any other particle that may be near them. And so they will start sucking in other ones, and as they grow and grow and grow and accumulate more of the matter, eventually they get to such a massive size that the gravity actually creates reactions with the material in it. And so there's our stars, and when our stars eventually die, which is not going to happen with our star anytime soon unless God wills it, our star would just turn into a red giant, and then into a white dwarf, and then into a black dwarf when it ran out of all of its energy to put stuff out. The really fun ones that I know you guys want to hear about is the massive stars, like Betelgeuse. Betelgeuse, if it were to go and die, it would turn into a red supergiant. Then it might go supernova, and it has two things it could turn into. One, it could turn into a neutron star, which if you've watched that Louis Giglio video, however you say his name properly, where he talks about like making music with the stars and whales, the neutron star is what he's using there. But there's also the possibility it could turn into a black hole if it has enough mass. And a black hole is something I'll put some videos out there for you guys about black holes as well. So that is the sequence. There's a really good page here talking about each of those things that you can and should read through. Black holes, I'll put up a really good video about black holes. Black holes, we don't know, we can't take a picture of them or anything like that, so we don't know that they're actually there, but you know, we have suspicions because of this bending of the laws of physics where we think they exist. So yeah. Here's a bunch of really cool stars out there that talk about where they are and how big they are and stuff like that, compared with our sun. Okay, so we're all pretty accustomed to seeing these things out in the night sky. I know every time when I walk out in a summer evening and I look, I find Orion right away. And and then you could find Ursa Major. These are asterisms. There's constellations and asterisms. So the Big Dipper is an asterism, whereas this constellation of Orion is so here's Big Dipper, which is the tail section of Ursa Major. So the Ursa Major is a constellation. The Big Dipper is an asterism. I'm going to finish this off. Hopefully I don't run out of time. Galaxies are like, okay, so there's the Earth going around our sun, and our sun is part of the Milky Way galaxy, and the Milky Way galaxy is a collection of billions of stars. And we're just kind of like this little thing out on the outer edge of the Milky Way galaxy. And there is a central disk of the Milky Way galaxy. I'll put up a really cool video as well of the Milky Way galaxy, someone taking a picture, but we've got these crazy pictures of the deeper parts of space. So I'm going to stop this one there, and I will finish this off next one. See you guys in a little bit.